Our coach just closed the door, so we can now begin officially. Today's speaker is Piero Rosati. He's our first Murray lecturer for this fall, and he's a very special Murray lecturer because he was very close with both Riccardo Giacconi and with Steve Murray. Piero's master's degree was on solar studies, which he got from Rome. His PhD and postdoc were from Johns Hopkins with Colin Norman, but at the time he was already working very closely with Riccardo, who was then at Space Telescope. He worked on the Chandra Deep Field South while he was there, and also on the Rosat cluster studies, Deep Rosat cluster survey. Riccardo then moved to ESO, and Piero then followed him. Riccardo then returned to Aura in the US, and Steve was then at Johns Hopkins, and that was the era of the Wide Field X-ray telescope, WFXT. Probably many of you have heard of it. And Piero would return at that time as a visiting professor to Johns Hopkins to work with both Riccardo and with Steve on the project. Piero then stayed at ESO for 15 years until 2013. In 2013, as you can see from his first slide here, he moved to the University of Ferrara, which is an older and venerable institution, founded in 1391, and at least one famous graduate is Copernicus, who got a doctor of canon law in 1503. Returning to Piero's accomplishments, he specializes in surveys. As I mentioned, Chandra Deep Field South, he worked very closely with Riccardo on the first observations. He also was the lead on the Rosat Deep Cluster Survey. He's now been working on CLASH, the HST project on clusters, and he also does detailed studies on clusters as well as surveys. And today, he's going to talk to us. His title is the same as I've written down, Exploring Dark Matter, Primordial Star Formation with Massive Lensing Clusters, and I give you Piero Rosati.
Thanks a lot, Phil. I'm really grateful for this invitation. To come to such an exciting place for me is always very stimulating.
Using the mic?
The mic, that's good. And I should say that I'm particularly proud that I'm part of this program, which is named after Steve, from whom I learned a lot over the years. So let me see if this works out. Okay, so today I'm going to, is he on? Yes. So I'm going to give you some of the highlights of the program, which is a combination of several observatories, Hubble, Chandra, and especially for the ground-based work, the VLT, for the spectroscopy work. And it's basically, just to give an introduction here, probably you know that clusters are quite famous cosmological tools that have been used in several areas of cosmology and extragalactic astrophysics to make advances. But we're not going to talk about what traditionally is the cosmological study, the use of clusters, which is to probe cosmology. People here like Alexei have done a lot on this using Chandra data. But it's in a way this is using the mass distribution of clusters across space and cosmic time to constrain our cosmological models. But today instead I'm going to concentrate on, if you want, on the complementary study that you can do not on gigaparsec scale but rather on a megaparsec scale with clusters. You can still use clusters and detailed studies of their baryonic and dark matter components to again test our structure formation scenarios. And this is because our lambda CDM preferred models makes really very specific distinctive predictions on the dark matter density profiles of clusters and also the structure, the inner structure of these of the dark matter halos which host then the galaxies that make the clusters. And so we can, if we use different techniques, which of course I'm going to go over during my talk, you can recover this information and then compare them with simulations. And particularly if you look at, if you find a deviation from the simulation, which obviously assume a collisionless cold dark matter, and for example in the high density regions in the core, where if, for example, the dark matter is not completely collisionless, there might be some observational effects. And then, you can also indirectly constrain the nature of the dark matter. So it's really fundamental importance. So then you get a bonus by using massive clusters, and the bonus is that they are really spectacular cosmic gravitation telescopes, which then you can use to look and unveil really distant galaxies, which otherwise you would have to wait for, 10, 100 meter, 30 meter telescopes, or JWST if you want. Okay, so just again in the introductory part, for people who are not into the cosmological simulations, just a snapshot in one slide, what are the main conclusions of Lambda CDM simulation and body-only simulation, which these days then obviously they're trying to include baryons to study the baryonic effect. But basically, these simulations predict triaxial shapes for galaxy cluster with the density profile, which is has a sort of a universal shape, meaning that you have just using two parameters, a radius, a scale parameter, and a density parameter, you can sort of reproduce all these halos from the galaxy scale, even dwarf galaxy scale, all the way to clusters. And okay, then other predictions are the logarithmic slope in the center here, okay, and this formula is used. This is not a magic formula. It's just the most popular fitting function, if you want, the Namarro-Franken-White profile, which is generalized to allow for shallower slope in the core, which otherwise would have a logarithmic slope of -1. Just remind you that around the scale radius here, and whose ratio makes the so-called concentration of these halos, the density profile, the logarithmic slope, turns over, becomes -2, like an isothermal profile, and then it's like r to the -3 in the outskirts. And then there are some scaling, shallow scaling of these concentration with mass and redshifts, which breaks this universality a bit, because clusters form a different redshift. You can think of setting up an observational program to test all this, but you have to do things really carefully. Just to show you, for example, the difference in concentration here between a cluster of 10 to the 15 solar masses and then another one at 10 to the 14 solar masses, very tiny. And also, you see, you want to cover the whole range. So it's if you want to really do meaningful comparison with simulation, you have to do things quite carefully. So what do we have to probe the mass of clusters of anything in the universe? Well, you just even think about general relativity. You have two ways, right? You can probe the space-time curvature around masses like clusters using stars, galaxies, or gas particles as test particles of these the gravitational potential, or you can use photons, right? You can look at photon trajectories and around these clusters to again probe the gravitational potential. I mean, this is obviously gravitational lensing. So this is what nature gives us, and we need to set up things to use them in the best way we can. And so, what are the requirements if you really want to recover with great accuracy and precision these density profiles and over 3 decades in radius? What are the requirements? The requirements are that, since each of these methods is not sensitive to the overall 3 decades in radius, each of these methods is good in a given radial range. Each method has its own inherent astrophysical systematics, and so you want to use all of them. Okay. For example, lensing, weak lensing, is pretty good at covering the outskirts of clusters. Dynamics is also galaxy dynamics, so basically using the galaxies as velocity, the velocity of galaxies as traces of the potential is again pretty good from 100 kiloparsec all the way to even beyond the Virial radius, as we will see. But this, of course, you have to assume that the system is in equilibrium in this case. And in the case of lensing, you don't need to make this assumption, but lensing is quite sensitive to a line of sight projection. So then in the inner core, the king there is clearly strong lensing, and I will talk a lot about this in my talk. And if you want to go really, really to the 10 kiloparsec scale or few kiloparsec scales, where you get into the BCG, the Radial cluster galaxy. So the only probe you have there, also strong lensing in some circumstances I show you, is internal kinematics of stars. So you want to use all of them, okay? And in fact, okay, in some over the last 5 years, there have been several claims which have found several evidence that there is indeed some tension with lambda CDM, especially when we look at the slope in the inner core and we look at the amount of substructure. Okay, so again, so just to remind you, what are the methodology? Well, one, dynamics, Jeans equation. You have two observables: is the number density profiles of galaxy, the Lineofsight velocity dispersion, okay, the radial velocity dispersion, and then you need to deproject that, and this gives you these two unknowns in the equation, and you need, there's a third unknown, because orbits, who knows what the orbits are like, so you need to have an ansatz of the level of anisotropy of the orbits, which is quantified, parameterized with this famous beta parameter. So if you have all that, if you have a lot of statistics, we'll see you can actually recover the mass density profile. There is a method which is perhaps the best method to solve this, which is basically it uses the observed, and what is the observed quantities are projected quantities. Okay, so you assume a model for the 3D distribution, the mass distribution, you project it, and then you compare the projected model with the projected phase space, observed phase space. Okay, this is the MAMPOS model developed by Mamon and Viviano and company. And so you can actually, you can apply this obviously out to the virial radius. Okay, then outside the virial radius, however, if you have a lot of velocities, you can still make this very simple plot, the projected phase space, just the velocity compared to the central redshift as a function of projected distance. You see there is this typical trumpet shape, but this edge is simply due to the fact there is an escape velocity, the fact that, galaxies have high velocity much higher than the escape velocity, you're not going to find them. So if you have enough statistics to see this edge, then you get the escape velocity as a function of radius, which is basically the square root of that is the square of that is the potential. So by doing this, you get the potential. Again, you're measuring things in projection. You need to have an ansatz on the. There is a parameter which is due to the anisotropy of the orbits. Okay, and then there is the well-known hydrostatic equilibrium equation for X-rays. So if you have great data like the Chandra data, and you can recover the density profile from the X-ray surface brightness, the temperature profile, then you can measure the mass, the mass of the gas and the total mass, the hydrostatic mass. Okay, there is one method. Which is particularly useful because it's the only method which, in a way, has resolution. So if you want, because I told you, it's not just profiles. It's also, if you want to compare with models, it will be extremely useful to have the 2D maps, the inner structure of these halos. So the only way you can do that in the core is with strong lensing. Of course, you can do that if you have a lot of what is called strong lensing features. In other words, multiple images which are split in the strong lensing regime. And if you have many of them, then you can invert the lens equation, and you can reconstruct iteratively. You can reconstruct with better accuracy the 2D maps, total mass of the cluster. Okay, which is schematically shown here. Right, and then, as I told you, as a bonus, you get the fact that you get an amplification and magnification of distant galaxies, which are the same, by the way, they use to constrain this model. So you understand these two science objectives come hand to hand. They just come together. So with these goals and methodology in mind, is the class survey was proposed originally with Hubble. One of this is now over in 2013. It was one of the 3 multi-cycle treasury programs. And at the same time, after a year or so, we launched this large spectroscopic survey with VMOS on the VLT, which is sort of to give the third dimension of the clash clusters, okay? And so the common goals, again, are really new, robust constraints on dark matter and baryon distribution in clusters and the discovery and characterization of very high redshift galaxies. So these are the key points of the VLT large program that I'm going to describe. So panoramic spectroscopy survey of 13, these are the 13 clusters in the south that you can observe with VLT comfortably for the 25 clash clusters. Redshift range between 0.3 and 0.6. Since we want you to recover dynamical mass profiles with unprecedented precision, simulations that we did early on with Andrea Biviano indicated that we needed at least 500 members to do that. And then, as I told you, it's extremely important to get, well, I'll emphasize this much more in my talk, it's very important to get the redshifts of these magnified galaxies because these help a lot the lensing models, both in the strong and weak lensing regime, because in the weak lensing you always have to be very, one of the problems with the systematics of weak lensing is that if you contaminate, if you don't select background galaxies, but you try to infer the shear contaminating your lensing sample with foreground galaxies, obviously there is a systematic, so it's important to have spectroscopic information. And then there is a lot of, I won't have the time to talk about this. Actually, there is Marianna Nucetella here who just came to Boston, who did her thesis on this. But there is a lot you can imagine that there is a lot you can do on galaxy evolution and transformation of galaxies and discuss it with all this information. I won't have the time to talk about this, okay? Now, in the last 2 years, there's this, I would say, not really exaggerating, phenomenal spectrograph, integral field unit spectrograph, which came online on the VLT. And I'll show you, this is, it's really, is a game changer in the inner core of clusters for a lot of these problems, okay? So, you know the clash, probably heard other talks on clash, but 25 clash clusters that were all selected to be massive with temperature more than 5 kV, and most of them, 20 out of 25, they were selected from the X-ray just to be relaxed clusters. Of course, as you know, there are no relaxed clusters in the universe, but at some point. But 5 of these instead were on purpose. They were selected to be really big mergers and large massive mergers, because you know that these are big lenses, and so these are the ones which are the best candidate to find high redshift galaxies. And so these are the 13 clusters that were followed up with the VLT. Okay, and then on the way, given the success of clash, because it was a success in many ways, there was a follow-up programs with direct recessionary time, with basically going back to the even other cluster, but doing 6 clusters more deeply in the near infrared. Okay, and this is the Frontier Field program, and again, a lot of multi-wavelength observations have been amassed on this, and particularly the Chandra program, where Christine and Steve led, and to get deep X-ray observations of these clusters, this Frontier Field cluster. I will concentrate actually on, I will show results from 2 of these. This perhaps tomorrow, in the 10 minutes talk, I will say something about this. Okay, in a snapshot, so what is the output of so the survey is over. Thanks to the fantastic work of Italo Balestra, we reduced all the 50,000 plus spectra. We have 33,000 redshift, so 33,000 more redshifts. Something like maybe 8,000 of these are cluster members. There are a number of hundreds of lens galaxies with spectra, lots of Chandra sources with spectra, because we try to put Chandra sources on the slits, and so on. So 10,000 of these redshifts have already been released in this cluster, especially to help the Frontier Field community. And this is the output. I mean, this is the number of spectroscopy members. Remember, the goal was 500. Okay, so we're doing pretty well. In some cases, several cases, we're actually exceeding the goal. In some cases, we're getting more than 1,000 cluster members, and I'll show the results on that. Okay, these are the clusters for which we have published several papers. Just to give you the feeling, so these are the 4 clusters. It's just a redshift portion of these 4 clusters. The red, obviously, are the cluster members, so that you get basically the in a snapshot, you get the value of this data set. Okay, you can look at the number of members and so on. Okay, so let's see, let's go through a number of these. So let's take Max 0416. This is not the best clusters to actually study the equilibrium profile because it's a merger cluster, but just to show you. So you start with this fantastic Subaru archival data, which are used for the weak lensing study, but also to select targets with spectroscopic targets. And just to show you here, in red are the clustered galaxies, which in this case are something like 900. This has been published and by Italo Balestra, and the paper, the catalog has been released as well. You see, you go all the way out to 5 megaparsec, so 2.5, even up to 3 times the video radius. Okay, then of course you have this beautiful HST data, and but let me show you. Okay, so and here. Thanks to the combination of the frontier field data, also the class data, and this new MUSE integral field units spectroscopic data, I think there's been really, we really drove a transition between what was like the standard strong lensing models up to 2 or 3 years ago, and what I like to call high precision strong lensing models, and this means that basically I show you what you need, but the crucial thing, what we understood now is clear. This wasn't clear a couple of years ago. A couple of years ago, people were trying to use photometric redshifts and color information to find candidate multiple images and then throw them into the model. What it turned out is fine at first level, but if you want to really have precision reconstruction of the mass maps, you really have to include bona fide spectroscopically confirmed galaxies, spectroscopic galaxies. And of course, before MUSE came, there were not many, so people were just trying to, do whatever they could with PhotoZ. But now that we have the SPEC-Z, we understand how crucial is to use spectroscopic confirmed galaxies. So this is 2 pointings with MUSE. MUSE then is a 1 arc minute field of view, so it's an integral field. So you have this. It's like doing X-ray astronomy in the optical, basically, because it's really, you have a pixel, 0.2 arc second pixel. From each pixel you can extract spectrum. Obviously you're scene limited, or you extract spectrum in 0.5, 0.6 arc second, but it's beautiful. So you can, go through the wavelength, and so there is a very good resolution. So it's high resolution, 2.6 Armstrong. And it goes all the way from 4600 to 9300, which means Lyman alpha redshift 6.4. Okay, and so the typical exposure times that are in the archive we got are actually most of these data are in the archive because there's a lot of GTO data that are going in the archive. People probably are overwhelmed by the data, so the publication doesn't come very easily. But between 2 and 15 hours. So this is an integral field, so you can make color image out of these cubes. This is a color image of the cluster. And okay, so it's not just all about finding background multiple images, but what is also crucial for doing these mass maps is to really have a robust, a pure and complete sample of cluster galaxies. Again, in the old days means 3 years ago, people would just do the red sequence, get a bunch of galaxies. But in the red sequence, you find a lot of galaxies which are not clustered galaxies. So, and again, in a high precision regime, you want to do this accurate. So this is what you could with MUSE. Obviously, you don't care, you get everything. It's not like slit, should I put a slit here or there? And here you can appreciate the advantage. This was, in blue is the redshift histogram. Sorry, it's not the redshift histogram. Is the distribution in magnitudes of the spectroscopic members that we got with the VMOS with very hard work, standard slit mass spectroscopy. And, this is with MUSE in 10 hours and much less effort from the data reduction point of view. You expand this and you get redshifts all the way, members, spectroscopic redshift all the way to 5 magnitude below M star, okay, down to 24, 25 and so on. Almost filling up the whole sample that you can build photometrically using these 12 bands, so you really have a very good photometric members sample. But most of this, 75% of these photometric members are now spectroscopically confirmed. So you can be sure that this is sorry, yeah.
color of the galaxies, I guess, because you still have the photometric.
Correct. Okay, exactly. When you go, this is just because when you go faint, you know, your spectroscopic the success rate goes down. So, okay. But still, compared to this, and I'll show another example, is a significant advantage. I mean, and I will show later, for many of these, for like 40 out of these 100 and so on, and more than 100, you can actually measure velocity dispersions, which you can imagine is quite useful. So this is what you can do on the background population. Actually, originally with Class VLT, we were very happy. We had something like 8 multiple image systems. You have to multiply more or less by 3 because most of these lens sources are split in 3 galaxies, at least this cluster for the mass configuration. So we were quite happy. And then GLASS came. GLASS is this HST GRISM program led by Tommaso Treu. And, you know, he brought this number of galaxy spectroscopic number of multiple systems to 15, okay? But then MUSE came, and you see there is this huge jump. And now, basically, we have more than 100, in fact 102, more than 100 galaxies, multiple images with spectroscopic confirmation, okay? So, and you know, it's completely polluted with constraints for your strong lensing models, real high precision constraints. And then there are also lots of interesting galaxy scale lenses system, but that's another talk. Okay, so in this case, you see, this is the number of families with spectroscopy redshift for the most famous massive cluster, the strong lensing cluster, have been studied over the years. This is just as a function of the area, the magnification area. But you see there is this big jump from 15 out to this, and this is really now the best cluster to do this. Okay, then, okay, so then you need to do your modeling. And so the strong lensing models, these parametric models, you assume so your mass is basically modeled with a coaddition of a cluster halo, so a cluster mass associated to the cluster halos. This could be, like in this case, it's 2 halos or even 3 halos, because we found, you know, that if you throw in another halo in the model, there is enough statistic to actually predict another small halo around this galaxy here. But apart from the details, so it's the sum of these diffuse halos, then the dark matter halos, the sub-halo population, if you want, the little dark matter halos which are associated to each cluster members, okay? And these are typically modeled with softer isothermal spheres, okay? Now, this is the standard thing we were doing until a year ago. So you do this, you throw it into your lensing inversion, and then you get the total mass, which here you see in white is the contours of the total mass, which is, again, the sum of this diffuse halo plus the little halos. But then we realized that by doing this, you know, by ignoring that there is actually 15% of the mass, which is in the diffuse component, which is clearly the hot gas, we were biasing our reconstructed diffuse dark matter halo mass. So we include now the gas mass into this as a prior, if you want, okay, into this mass that you can get very accurately from this beautiful Chandra data that, you know, being presented by Green, and this is Christine's work and so on. And then, you know, at the end you get you get basically a full 2D distribution of the total mass, the gas mass, and and with these models you can reproduce the positions of these multiple images with an RMS accuracy of 0.5 arcsecond. Okay, so that's the thing. Until 2 or 3 years ago, you could reproduce the positions of the models were reproducing the position of the multiple images at 1-2 arcsecond RMS. So in this case, instead, this is the high precision regime. You have really a few tenths of arcsecond, and with which you can reproduce and predict the observed multiple images. Okay. So, and then when you have that, you can have fun and look with really, you can at least trust the robustness of these profiles, baryonic profiles and dark matter profiles, different baryons, gas and stars. And so, for example, you can measure the baryon fraction, you see the star and gas fraction, and you see that it climbs up to a larger radii. It climbs up to the global value of 15%. But I told you that one of the big issue was the slope of the dark matter in the core. So how do you get that? By basically you take the total mass and you subtract the contribution of the baryons, and then you find that indeed the dark matter, at least the diffuse part of the dark matter, seems to be shallower than the NFW predictions. So the total mass is, in fact, the total mass in the core is even steeper than NFW, because there is a lot of baryons in the core, particularly the BCG. But if you subtract this accurately, then you find that this is shallower. So this is one of the tensions that I've been talking about. And then, of course, when you have these maps, you can look at the 2D structure of this fraction. For example, here's the gas over total, the gas plus stars over total. And it's interesting because you can now do really this comparison with simulations which are reaching this level of resolutions, okay? But so the surprise came when we looked in detail at the subhalo population, okay? So because the lensing model gives you the mass of all these little subhalos, apart from the diffuse halo, and then you can just look at the mass function of that, okay? And you can compare them with simulations. And so there we found quite clearly, at least in this cluster, but now this is coming also for the other clusters, that there is in excess of massive subhalos, so massive galaxy if you want, in the data compared to what the simulation predicts, okay? This is the number of, so the distribution of the number of these galaxies is a function of the circular velocity, which is the square root of GM over R in the simulations, which we probe with the effective velocity dispersion of these halos that you get from the best fit of the lensing data. You see that basically the data, so in the simulation there is a lack of massive subhalos. Where do they live? Well, obviously they live mostly in the center, okay? So this is the distribution as a function of the projective radius. So there is this lack of big halos in the simulation. How come? Why they didn't form in the simulations? One of the the theories are looking at is some way of that tidal stripping could actually lead to the destruction or not formation of these massive subhalos. But these were n-body simulation, dark matter simulation only. So many people thought, well, once you include the baryons, maybe things will change. And people have tried, and we have looked into this with a cluster, actually nearby cluster from the Sloan. We have velocities from the Sloan, and this has been compared to baryonic physics simulation, which include the baryonic physics. The things improve a bit, but there is still a significant mismatch between the subhalo mass function observed and the one in the simulation. We still don't understand. We don't understand this. Now, of course, one of the things I say, but how do you really can trust these masses, from the masses of the single galaxy from the lensing model? After all, you just assuming the light traces mass and so on. There's a lot of assumption there. So, but here, the velocity dispersions are very helpful, okay? Because I told you, with μ's, you can measure velocity dispersion down to 22 magnitude. It's pretty good. So at that point, we did that, and you can compare the mass that comes from the velocity dispersion, okay? So sigma square is GM over R, and with obviously measuring the effective radius from the HST data. And these are the data points, these blue data points are the observed, the mass is inferred by the observed velocity dispersion. You compare it with the best fit lensing, okay, model, and you see it's not too bad. So this is in a way corroborates that this mismatch is there. Now let's go to more relaxed cluster, because there we can really look at these density profiles. Okay, this one is actually the first cluster that we study in Clash in Max 1206. This is not a frontier field. It's not a frontier field okay, and data. But it's again, you have all this beautiful Clash data. We have, in this case, originally we had 600 members, and so this is the first comparison reconstruction of the mass density profile we did for this fairly relaxed cluster. And then I show you how we improved dramatically the data. But this already was pretty good. So the strong lensing and weak lensing agree quite well. And this is, no, they don't talk to each other. These are completely different data and methodology. And then, if you look at the dynamical mass profile recovered from a combination of the Jeans equation and this caustic method which I described, this is what you get, is this gray plus a green, okay? It's a pretty good agreement. Then you can, this is an NFW fit. It turns out actually NFW is a pretty good fit to the overall cluster, okay? Cluster mass halo. I mean, the problem arises in the core, okay? And then you can look at the Chandra data, which these are shallow Chandra data, 30 kilosecond. Unfortunately, we got time this last cycle to get another 130. We're really looking forward to that. And I see also the Chandra data originally looked quite in good agreement. Remember this hydrostatic bias that probably you heard about? We'll go back to this. Okay, this is, then we look at the Muse data recently. This is a paper just been accepted last Friday led by I should have mentioned him earlier, but led by Gabriel Bartosz-Kamienia, who is a postdoc of mine in Ferrara, who is now going, unfortunately, to Groningen next week. And so in this case also we got lots of multiple images, but perhaps the exceptional thing about this cluster, in clusters to get radial, so-called radial images, these are multiple images which are very close to the core, which is very useful because we want to constrain the core in the center. You need to have this extra. So you're lucky if you get one, okay? Not even two, one in many clusters. In this case, we found something like 11 multiple images within 50 kiloparsecs. So the central core is polluted by this multiple image. This is great news if you want to really reconstruct the mass all the way to there. You see how difficult, what is the difference with Muse, right? These things are not even visible in Hubble images, okay? But if you look at, you go through your cube, and you make a narrow band, you're just going through it, and you find these Lyman alpha emitters. This is the Lyman alpha, the narrow band image, if you want, okay? And it's an obvious narrow band. This is a Redshift 6 Lyman alpha emitter, okay? Which you will never even, well, you don't even see it in HST, so obviously you will never find any kind of spectroscopy. So in this case, then you can really reconstruct very accurately the mass. This is the enclosed mass as a function of projected distance. You see the strong lensing model compared to the dynamical model from the old data. And again, you can do the usual thing. You can subtract the contribution of the baryons. And in this case, you see, you get a slope. If you measure this slope, is around 0.6, 0.7, 0.8. So it's the dark matter slope. The slope of the dark matter density profile is indeed a bit shallower than NFW. But as usual, when you have very good data, then you understand the problems you had before when you didn't have this. So it's to measure these slopes. It's really you have to be really careful. And for example, we found out that if we hadn't had all this number of multiple images in the core, we would have get a bias estimate of the slope. So again, you need the best data. Even when you have the best data, you have to think about it, okay? And this is the best work in this field was done, but again, with data of, I would say, the previous generation by Newman et al., which they found for a sample cluster that indeed the dark matter density seemed to be shallower than 1, which is the cosmological simulation. Okay, just to show you that it's not by chance that all these probes give you the same answer, let's look at another cluster. Again, it's nothing is really relaxed, but it's quite well behaved. This is a frontier field cluster. These are the, again, this is you can look at the phase space, and again, Muse data. Muse data, you see, in this case, we've got plenty of multiple images, but none really in the core. So it's not, but still, it's lots of constraints for your lensing model. But here we can do more, okay? If you can extend the dynamical constraints to the very core because I told you, basically you run out of galaxy 100 kiloparsec, okay? So below 100 kiloparsec, you don't have enough to measure the velocity dispersion of the galaxy velocities. used as tracer of the potential. But, with MUSE, I told you, it's like X-ray astronomy. So you can do a sigma profile. In this case, unfortunately, the BCG was cut in half in these two observations, so it took some time. It took me to extract this. But I mean, the structure on one and the other side of the galaxy are very consistent. And you see, you can measure the velocity dispersion as a function all the way up to between 2 and 3 times the effective radius. Then you can model, you have a dynamical model. You model this potential here, basically with the two contribution, the stellar mass of the galaxy, which you know quite well because you have the stellar surface mass density profile. You use a Jaffe because a projectional Jaffe model is the vacuolar profile. Then you can use a generalized NFW to model the halo, the cluster. And so by doing this, you get a pretty good fit. You see, this is work that Barbara Sartoris is doing in a paper in preparation. And so by doing this, basically, you can constrain the total mass from dynamics all the way down to basically 1 kiloparsec, okay? And this is what you get. I mean, it's not cheating. Because if you look at papers from 10 years ago, these profiles were all over the place, okay? Again, and then people, as usual, when things are all over the place, people, instead of blaming the data, they blame nature. And they start saying there is retrospective bias, there is this and that, and so you see in this case, the weak lensing, you can even think weak lensing catches up here to the right value, but here these are not Subaru data, wide-free cameras. These are 2.2 meter ISO because it's too far south for Subaru, but still, you have to zoom in to really see the difference here, especially in the core, where I say now you can have the dynamics all the way with the BCGs. These dotted points, just to tell you, is the dynamical profile that you will get without using the BCG. So you say it would be a bit biased. But I mean, that's what you see. Everything is really on the top of it. So again, all probes agrees. I don't see any hydrostatic bias. The hydrostatic bias in cluster was invoked immediately when they found this mismatch of the cosmological parameters between the Planck cluster cosmology and standard parameters, and again, you can get the calibration wrong. You can attribute the wrong calibration between mass. For example, in SZ, you can call it hydrostatic bias, but actually, it's something else. Now, in this last 10 minutes, let's look at this, because I think this is quite exciting. So it's the complementary part. I told you these are gravitational telescopes. Now, all this work of doing high-precision lensing is actually very useful for this too. In fact, I told you that you need so many of these high-redshift spectroscopically confirmed galaxies to constrain your models, but at that point you have this great sample of these galaxies. And what is the advantage of using gravitational telescopes? Well, these are narrow-field telescopes, okay? So in other words, you get magnification of up to 10 or 20 or 30 in small areas of the sky. So these are great if you want to unveil and study population of sources which have high density. So it wouldn't be good for X-ray sources, unfortunately, because the surface density of X-ray sources is not that high. But for blue, high redshift galaxy, there are plenty of them. You actually have a big advantage, a big bonus in using this large narrow field gravitational telescopes, okay? But again, if you don't have these good models, you could never trust, because at the end you need to demagnify, okay, these things. You could never trust the luminosity, the star formation rates, the stellar masses, the sizes, the luminosity function. To do all this, to do all the physics, you need to have, this is why the two. Okay, but then don't forget that it's not just amplification, it's also magnification, okay? So surface brightness is conserved in lensing, so amplification comes with magnification. This is great because if you do if you look at the typical HST pixel and you throw in the typical magnification of 10, you see that basically you have pixel on the source plane, you have pixel of 20 parsec, between redshift 3 and 6. So if you really can trust the size of these things, you can really, you can probe a few tenths of parsec, not kiloparsec, at redshift 3 and 6. Okay, and what is the importance of this, of unveiling and boosting up these faint galaxies? Because we all believe that faint galaxies, because there are many of them which make up the luminosity density, the high redshift luminosity density of galaxies, and because they are thought to have a high escape fraction, these galaxies are thought to be the main drivers of ionization. So you really need to understand their physical properties and their abundances to really verify that. So this work was done so far just photometrically. I mean, all this luminosity function you heard of, high redshift, is all photometric, okay? So this is this cone plot which compares the class VLT, this blue and red is the class VLT redshift, with the Muse redshift of these two clusters which I described. You see, you have this pencil beam, extremely deep. Well, I'll show you now that you go really deep in the luminosity. You can do this because you have all these emission lines which happen to be, which by the way, they're all split with Muse, so you cannot mistake them. And you know, they are just the way they are. You can cover the whole redshift range. There is no redshift desert, if you want, from redshift, you know, behind the cluster all the way to redshift 6.4. Okay. So look at the luminosities. So this is the Lamin alpha region, right, between redshift 3 and 6. If you look at the Lamin alpha luminosity, this is the typical field values, around 10 to the 42 per second. This is from the HDF South with Muse. Again, the data from the Chandelier Field South are coming out soon. And you see, with the lensing, obviously, you go much fainter, okay? And so now we have something like 100 of these Lamin alpha emitters on the source plane. And, you know, these have fluxes of 10 to the minus 19. So if people have done narrowband image work in the past, they can appreciate that. Equivalent widths are very high, between 20 and 200 or so. And I'll show you now in a second that the stellar mass that we are probing in this case are very low. We go in the 10 to the 6 regime, 10 to the 6 solar mass regime. So if you combine these three frontier field class cluster with this Muse data, you have basically on the plane of the sky 6 arc minutes, 6 square arc minutes, which basically means that you have 1 square arc minute magnified by 2 magnitude, okay, on the source plane. So you have it's small 1 arc minute, but there's still a lot of stuff. In fact, look here. This is the distribution, just the magnitude versus residual distribution of the class VLT that really was a hard work to get. And, you know, obviously you have the spectroscopic limit, the famous spectroscopic limit at 26. And then, you know, Muse came, and you say this is observed magnitude and not the lens. You can extract spectra and measure redshifts from emission lines all the way to 29 and 30th magnitude. I mean, I couldn't believe it myself in the first case, but because the continuum width is quite high, you can see here, the continuum magnitude are faint, but since this Muse has this high sensitivity, line sensitivity, you could do that. Then if you delens this, we know, you know, we have these models, we know the magnification, and this is what you get. The intrinsic magnitudes of this population we unveiled is something like, you know, 32. So you are in JWST regime. And some of them we haven't even estimated because you cannot even see them in the frontier field data. So, you know, they can be even fainter. Okay? So all this work that's been done on the luminosity function purely photometrically, now we can start really probing with spectroscopy, start getting some physics out of this, okay? And just to give you an example, there is a series of papers that were published, led by Eros Banzella, on these objects, the physics of these objects we have derived from the spectra. And here, I just show you here, this is a little movie that goes through the Lamin alpha redshift 6.1 for this arc. You see the arc coming out there, there, okay? And so then you can look at detail. This is the Muse image of this arc, and you can look at the numbers, okay? So this observed magnitude of 27.9 with a magnification we see of 25 plus or minus 3, and this arrow, you know, we work very hard on these arrows, and we're talking about then observe the lens magnitude of 31.4, which this is an important number. We're going down the luminosity function to minus 15, okay, spectroscopically, okay? You can derive the sizes with then also a lot of simulation to see the robustness of this. And the size of these objects, for example, this little clump here, see this what we call GC1 here, it's 16, 20 parsec, okay? The ages are a few mega year. I'll show you a bit more about this. Star formation rates are not high, but the specific star formation, the star formation rate divided by the mass, is extremely high, okay? Okay, but all of them, these 3 or 4 of this system we have studied in detail, they all seem to have companions. So clustering, we don't know. But the thing is that people have been thinking, especially with now the JWST is coming, people have been thinking about finding the progenitors of globular clusters, okay, and in the high redshift universe. I mean, we know the globular cluster today, we know their stellar population, but there are several models which predict that a first generation of stars have to rise around redshift between 5 and 3 to then, with a second generation of stars, lead to the cluster, the globular cluster that we know, the very old population that we know today. And so, if you look at the models, this is a discussion that was stimulated by chats with Javier Renzini, who has actually been studying this and see how you could do this with JWST. We actually realized that the sizes, luminosities, star formation rates, all this, are consistent with, what the models for the progenitors, for the precursor of globular clusters are. So we think that we speculated that this could be, because we don't know what these are. What are these dwarf galaxies? These are big star-forming regions, a high redshift, but we don't really know whether they're dwarf galaxies, or perhaps they're progenitor of globular clusters. Just that's to give you, then I finished. We went through the modeling of the spectra and SED of this galaxy. This is a paper led by Carman in 2017, actually. And so, again, I told you, you find specific star formation divided by mass function ratio. If you compare it, for example, for candles, so-called red sequence, this is called red sequence, you find it is well above the red sequence, all these galaxies, or whatever they are, we call them. So this means that basically these galaxies double their mass every 20 mega years or so, okay? And if you look at, I told you, the ages and stellar masses, we are down, to a few 10 to the 6 solar masses with ages of a few mega year. So really, we are a completely different regime. Again, you can see there are very continuous slopes which are very steep, so very likely very low dust content. And there's also been some Laminar alpha modeling that was done to try to understand the circle galactic medium about this. They seem to, all the evidence points that this could have a higher sky fraction. So, all the evidence are there, but definitely not the final evidence that this could be the good contributor to ionization. But actually, we don't know what they are, right? We don't know whether they're called a galaxy or what. So just the final slide and outlook. There is still a lot to do with this combined data set. But definitely, I told you it's a gold mine for galaxy evolution. But definitely, we went into a regime where we really can start looking at the detailed structure of these halos, both their baryonic and their dark matter components over, from kiloparsec to megaparsec scale. I told you that this spectroscopy is critical to really address issues like, is really flat the central cores or what? The intrinsic physical, from this it's critical because you can get the intrinsic physical properties of lens sources. And there is actually, if you want to do better than this, you have to start thinking about line of sight effects in these lensing models. Now these models are so good that actually you see that sometimes if there is a galaxy, a foreground galaxy which is not too far in projection, you see that actually the prediction of the position there is not as good as the other one. So you can really feel that. And I told you that with this data, we have sort of entered this new regime where we can see this low luminosity magnitude, UV, absolute magnitude -15, galaxy with very low stellar masses. And really, we're getting the first glimpse of the physics and the astrophysics that we'll be doing with JWST in a couple of years and 10 years with ELTs. Okay, stop here.
Okay, go ahead.
So I'm not sure the fact that you're finding something better than -1 constitutes any tension percentage at the end. And secondly, when you have these subhalo mass functions, it's recently been pointed out that overmerging and numerical disruption in these simulations is still really rampant and could easily give you a factor of 2.
For mergers, in mergers, you mean?
I'm talking about numerical disruption.
Right.
Which is purely numerical.
Okay.
Reduce the number of subhalos in the simulation by like a factor of 2. So what you're finding maybe is not at all in tension with real lambdas at the end.
Okay.
He's finding more.
But
He's finding
so I find it more.
Yeah,
You have to destroy them.
It's finding more than the simulation. If the simulation does overly disrupt the subhalos, then that's compatible, right?
So-
People are used to having this missing
Right, okay,
problem.
so-
It might be the opposite problem.
Yeah, this is opposite problem. This is it's not the missing satellite problem. In fact, so obviously, this is. I've been talking a lot about Stefano Borgani and all the simulators about this, and they cannot really understand. At some point, they will say, "Are you really sure?" Then, and I haven't shown this because it's working properly. Now we have the sigma function, the mass function from this data. Okay. And the mass functions really show that there is excess of big things. Okay, now people theorists said that these sort of effects they seem to be beyond this mismatch. Something that, for example, Klaus Dolog thinks is that also Stefano that perhaps once we include baryonic physics, which reduces the slope in the center, and then we'll go back to the slope. Then, if you have a shallower, if you have a flatter, puffier cores, this should be more effective via tidal stripping at destroying these halos. So maybe you say when you will solve the other problem, then maybe you will solve also this problem. We are really, at this stage, we are really in the early days on this. I mean, at first I was actually cautious on this. Now we look at the other cluster, we look at the velocity dispersions. It's hard, I don't know, they're there. For the internal slope, there you have to be very careful. Because, I mean, again, if you use a model, okay, you can fit anything, even to this fantastic, data, you can fit actually, okay, it's very, if you assume a model, you can actually get different answer. Because as you said, you get a gamma of 0.7 with an FW, but then you fit an ASTO, which is flat, and it fits. So then I think we need to get into a point where we compare. So what we can reliably measure here is the projected mass density, and if you want, the projected logarithmic slope, okay, as a function of radius, whatever it is. I don't want to fit anything because it's dangerous. I just give you the projected, so the derivative of the projected mass density profile. And this is, at that point, you have to go to the simulation, and you just show me the same thing without fitting. So perhaps we think this is the best way to do it. But again, now that we have these results, we need to go back to the simulation and we can discuss this. There's more to say as we get technical. And
No more questions? So just to pick up on that point again. So do you know if in the Newman analysis, when the slopes are inferred, how the orbital anisotropy is treated? As in, do you assume isotropic orbits for that? Because in simulations you actually see that the orbits are anisotropic as a function of radius.
You talk about the stellar kinematics? Yeah, exactly. There's been a paper recently by the Darwin group addressing that, saying that in the analysis by Newman, the isotropy, the orbits are taken isotropic. Okay, so it's beta 0. Okay, just to make it easy. I mean, after all, those data, remember, it's a really the velocity dispersion. I mean, the constraints, the multiple image are like 4 or 5, not 100. The sigma profile. So there are very few times you get these radial images. The sigma profile comes. I mean, the data are not as good as. So they went for the easy dynamical modeling, and they assume beta equals 0. You're right. That's one of the claim is that this mismatch might be due to that. So in this velocity dispersion profile dynamical model I showed, actually we don't assume a beta. We put a beta profile, and what you get is that the model prefers isotropic orbits. Okay. I'll tell you more in, we are working on this, but we definitely don't fix beta we try to get, but and there is definitely some leverage in constraining beta with this data. It's not just that you have to assume it. Now, whether that's the reason of the mismatch, you have to think about projection effects, okay? Because again, this is all spherical, and the projection effects can give you a factor of 50% easy for what I understand. So but we have the accuracy now, that we have the data quality such that you can actually look at these things. That's the hope.
Thank you.
So in the substructure analysis, do you essentially keep masses at the location of cluster members?
Yes.
Do you have enough information to look for additional
On the subhalo, okay, on the subhalo cluster population, for the general cluster, we actually, for example, in the cluster 1206, we have only one halo, and then we just threw in another couple of halos, and they could go anywhere, and they actually, what they did, they of course created a mass distribution which is not even elliptical, it's asymmetric. At that point, the RMS went from 0.9 to 0.4 arcsecond. So this is telling you that at the level of the diffuse dark matter, you can actually play this game. You can throw, just add multiples if you want. It's interesting that you're asking this because I actually would like to try to not assume, first of all, that mass trace is light, and second, that you just nail your subhalos on the. And so the way to do this, and we're looking to this, is to use not just PCs for do this, because these models are more inverted with like 20, 30 cores PCs. Now, if you get a big machine with 1,000 of cores, then you can explore that kind of parameter space that we never even dare to explore now. So we had a discussion on this.
I want to follow up your question a little bit more. So suppose you used, in any of this analysis, you actually use the X-ray surface brightness? So, I mean, as far as putting in extra masses?
In this case, we do. So we found that, in fact, that's an interesting question. I mean, because at first we were just ignoring X-ray, and then we thought, but by doing this, the diffuse halo mass that we find is biased, right? Because there is 15% of stuff in there, and in particular, a big deal here is to see whether there is an offset between the dark matter centers and the galaxies. Because if there is an offset, well, And so there's been a lot of claims there, which then have been disclaimed, have been retracted. In this case, there is an offset of a few arcseconds. So we never claim anything because we understand the limits of this systematics. But in particular, we figure that by not including this big baryonic diffuse component, we were biasing the 2D. And so we're doing this with Mario Bonamigo, who is a student of Claudio Grillo. We are actually doing this systematically. So the gas mass is derived from the Jandro data, okay? So the surface brightness is fit. Well, I can tell you technically, but we do it. But I mean, and then this is put into as a prior into the lensing model, so that the diffuse dark matter component that you derive, it's not biased anymore. And we find indeed that this offset is not significant in this case. I mean. So that's the way we're doing it now.
So do you go back, though, and make sure that this mass model is consistent with the X-ray surface brightness distribution?
Oh, yeah.
You don't need any other mass components?